I'm Sam, and I'm a philosopher, and this is Eric, and he's a physicist. And today we're talking about the scientific method.
Although the phrase scientific method existed in the middle of the 1800s, it really came to be known. It came to be known as a very specific sequence of steps in the early 20th century.
Hmm,
Okay, where it
okay.
started to appear in textbooks. Okay, so do you remember learning it?
Oh, absolutely. I don't know if I remember what it was. You could quiz me, but I remember learning it for sure.
I mean, the steps. The steps are something like make an observation. I mean, I think it's simplified, but you make an observation, make a hypothesis to explain the observation, design an experiment to test whether the hypothesis, to test the hypothesis, and then use the results of the experiment to refine the hypothesis. And then the idea is that you just keep repeating that series of steps over and over, refining your hypothesis until it becomes, I don't know, publishable or something that people care about.
Okay.
There are some, there are some things that are probably obvious, like really we're talking about a set of observations, maybe even a wide set of observations. And then and then there's a whole separate discussion in middle school about, how do you design a controlled experiment, which we won't get into here. So nevertheless, that was for people in our generation. I think for people even in my son's generation, this was the standard. This was the standard way of teaching how science is done. But today, I wanted to go through some historical examples and maybe some examples from my own life, if there's time, and see the extent to which the scientific method, as we learned it when we were kids, matches up with the way scientists actually do their work, or the way science actually gets done. The first example I'm going to give, I think, is pretty much one of the purest examples of the scientific method as we learn it that I could think of. Okay, and this goes all the way back to Galileo in 1610. Okay, so I mean, our listeners probably know that Galileo eventually got into trouble. He was accused of suspected heresy in, I want to say, the 1620s, and eventually put under house arrest for the rest of his life. But he before then he published a book called The Starry Messenger, Sidereus Nuncius, in 1610. And he laid out a series of observations which were very simple and which revolutionized the way everyone thought about the solar system, which wasn't really even thought of as the solar system at the time. Because at the time, before he published his work, most people believed that the Earth was at the center of the universe and that the sun and the moon and the planets and the stars all revolve around the Earth. What Galileo did is he didn't invent the telescope. He did refine and make his own telescopes, and they were generally better than anyone else's telescopes. But he was the first person who pointed his telescope up at the sky. Okay, so until then, the telescope was mostly used in military situations. Also, if you were a merchant and you wanted to know when the next ships were coming into port, you could station someone in a tower with a telescope and tell them to watch the horizon for incoming ships. But Galileo did help with those things too. But what he did is he let his native curiosity prompt him to point his telescope up.
I mean,
And,
surely like other people did that too. Right?
I mean,
I
it
feel like
seems okay. So to you and me, it seems
had to
super
have done that.
obvious. I mean, he made most of his discoveries at nighttime. If you were a military scout, you would be, I don't think you'd be pointing your telescope up at night. If you were being paid, if you were a merchant or a merchant scout, I don't know. I mean,
Yeah. I don't think
so you're
he's maybe
thinking
the
that
first
just
person who was in a position to like do systematic observations or do science with that. But I'm sure someone like checks stuff out with their telescope.
Okay, I guess, I think at the time it's worth remembering that telescopes were probably incredibly valuable and incredibly rare. So I think that part of the issue would be, who had access to a telescope. It's not like they were just floating around on the street or something. But I mean, actually, it is a good question. The question of untold narratives in history and untold narratives in the history of science is something that is getting more attention nowadays. But I don't know. I don't know any of that. So let's talk about what Galileo saw and what he wrote down in this little. And he had some wonderful sketches too. What he put in this little. It was almost more of a pamphlet called Sidereus Nuncius, or the Starry Messenger. Okay, so remember, at the time, although the idea that the Earth moved around the sun had already been proposed by Copernicus, that idea was banned by the Catholic Church, which had a huge amount of power in the Italian peninsula. Galileo, one of the things Galileo saw is he pointed his telescope at Jupiter. Now, through the telescope, Jupiter appeared not as a point of light, but as a small disk. So instantly he could tell that it was a planet and not a star, because no matter what telescope you use, stars are points of light. So he could tell Jupiter was a planet because it appeared as a disk. But around the disk, as he made repeated observations night after night, what he saw was Jupiter was always accompanied by 3 or 4 little stars, little extra points of light. And they were always in a line with the equator of Jupiter. And from night to night, their locations of these 3 or 4 stars changed, but they never got too far away. And there seemed to be some predictability in their motions. Okay, so it wasn't like the motions were completely random. And after a couple of months of observation, Galileo was 100% certain of what he was seeing. So, Sam, based on my description, do you want to guess what he reports or what he hypothesizes?
Um, well, I'm trying to remember what I know about this, but just based on that, did he think they were actually orbiting Jupiter?
That's exactly what he concluded. Right. So he said, you know what? These have to be, Jupiter has moons, and these moons orbit Jupiter. So, I mean, it's an explanation which, when you see his pictures or when you see modern pictures, it seems super obvious. But this was absolutely revolutionary. Until that moment, no one had ever seen clearly objects orbiting something other than the Earth, right? Remember, I mean, we now know that the Earth orbits the sun, but you could, from a subjective point of view, you could try to build a cosmology in which the sun orbits the Earth. And in fact, that was the standard cosmology for thousands of years. But Galileo saw these little stars, and they never got very far from Jupiter. They were clearly something orbiting Jupiter. And this, I mean, the minute he published Sidereus Nuncius, it was the beginning of the end for the sun-centered system. Because for the Earth-centered system. Because if the Earth is, how could you possibly explain these little stars if the Earth was the center of all orbits? So this was just one of his many discoveries. I mean, I can give you a couple of others that seem really, maybe even more obvious. He discovered that Venus had phases just like the moon. So there are some, if depending on the time of year when you look, Venus might look full, which means that Venus is on the other side of the sun from us, and it's being illuminated by the sun, and we're seeing most of it. Sometimes through the telescope, Venus looked like a little crescent, okay, which means that Venus is on the same side of the sun as we are, and so we're mostly seeing its dark face. Okay, so again, that's evidence that Venus is orbiting the sun. And then he pointed his telescope at the moon, and he saw craters and mountains on the moon. Actually, people often think that they can see craters on the moon with the naked eye, but actually, even the largest craters might appear as blotches, but with the naked eye, you can't tell that there are ring-shaped mountain ranges on the moon that we would call craters. Okay, that requires a telescope or binoculars. You can see something with binoculars. So he found these really obvious things in the night sky that no one had ever seen before. And he published them, and they were basically beyond dispute. I mean, so Sam, you're a philosopher. You specialize in dispute. Having heard these 3 sets of observations, could you I mean, what's your take? Does that like if you see the shadows, if you look at the shadow on the moon and you see little hill, you see what looks like pretty obvious hills and valleys. Is there an alternative explanation you could field, or does that seem like one and done?
I mean, it's hard to think of a reasonable explanation. You can clearly come up with unreasonable explanations.
Can you think of an unreasonable explanation off the top of your head?
Oh, sure. Yeah, they're aliens on the moon. The moon is a completely featureless, smooth ball, but they have little cutouts. And so they do little shadow puppets and make like
Oh, so
shadows of the various things.
so this would be like a legit conspiracy theory where there are intelligent beings who are trying to trick us.
Yes.
Um, that you could also imagine. I've read at least one source, but I haven't checked the historical accuracy that that you could propose that what we were seeing was not the true surface of the moon, that the true surface of the moon is perfectly smooth, but it's also perfectly transparent, and so that we were seeing deeper, uneven layers of the moon.
Oh, that's a good one.
Yeah. Um, and so and I think that the Catholic Church was the dogma of the Catholic Church was really based on hypotheses that were thousands of years old at that point. And so they believed that the moon, I mean, even though you could see with the naked eye that the moon has blotches, it was sort of, again, it was somewhat controversial to claim that the moon was not perfectly spherical. And again, I mean, the reason it was controversial to claim that things that the sun might be the center of our solar system is that I think there's a moment in the Bible where it claims that God extended the length of the day by freezing the sun in its orbit across the sky. In particular, there was an ongoing battle, and God extended the length of the day so that the good guys could have extra time to wipe out the enemy. Uh, so right. So it was one. So, I mean, so Galileo, the minute he made these observations, he had to begin a sort of delicate dance with the Roman Catholic Church where he was allowed to make certain kinds of statements, like this is what I see through the telescope, or this is one possible explanation. But what he wasn't allowed to ever say is this contradicts the Bible. Right. So he was supposed to leave wiggle room for the church authority, the people in the church who were responsible for religious doctrine. And so eventually he ran afoul of those people, and he was, like I said, he was ultimately imprisoned. But nevertheless, I think that this is one of the cleanest examples where a new scientific tool it essentially immediately revealed things that no one had seen before, and which were also very readily interpreted in one very intuitive and obvious way.
Sure. Although I will point out that astronomy is not, at least in that time, was not an experimental science. So he couldn't design an experiment
Oh, right,
to test it. So there's still
right,
that element of the scientific method,
right. So
so-called.
you're right. So I picked an example which I thought was really obvious science, but right, the scientific method says make an observation, which is we see these little stars,
Yeah. Okay.
Jupiter.
Check. Check.
Propose a hypothesis, which is that Jupiter has moons, and that's what we're seeing, and these moons orbit Jupiter. Oh, you're not going to give me a check for that one?
Okay. Check. Yeah. Well, I
Okay.
already did the check. I did check. So I was
Okay. Oh,
anticipating.
okay. Right. But then step three of the scientific method is do an experiment,
Yeah.
right? So that falls flat,
Yeah.
or yeah.
I feel like we've done it now. Like, I think probably like having a spacecraft orbit Jupiter and see the moons and watch like that
Oh,
probably
okay.
counts as an experiment. But
Yeah. I mean, right.
Galileo
So
wasn't doing that.
additional. Okay. So I would argue. Let's see. So if we actually, you know what? We've landed things on. Oh, you know what? Actually, darn, I should have reviewed for this. Um, I think there was a
No.
Titan lander. I'm not
Yeah.
sure we've
Not a
landed.
no. Not on
Titan is a
Jupiter's
moon of
moon.
Saturn.
That's right.
So we've landed on one of Saturn's moons, but that wasn't one of Galileo's initial observations. Yeah, through the telescope, Galileo could see that there were these kind of cloudy lobes to either side of Saturn, but he couldn't quite. His telescope wasn't quite good enough to discern that they were sort of the things that you or I would call rings.
Mhm.
The ring hypothesis happened later. Um, So on the one hand, that's an early historical example from the early 1600s, which is a very clean example of what scientists do. They invent a new tool, and then they apply it they use it to look at something no one's ever looked at before. And simply making those new observations is pretty much very clean science. Often, not always, maybe not even half the time, but often what you see has one unique interpretation that pretty much any person would agree, oh, that's common sense. It's just common sense. We're seeing moons on Jupiter. Moons on the moon. It's common sense. We're seeing things orbiting Jupiter. Did I say moons on the moon or mountains on the moon?
You said moons on the moon.
Okay, that's what I thought. See, this
So I
is
knew
what
what you
happens
meant.
when we
I knew
record in
what
the
you meant.
morning. Okay, mountains on the moon. All right, but that is one. So it's a historical example which also illustrates something which still happens today. We design a new tool and we use it to make fairly obvious explanations of things. All right, let me give a second historical example where things are trickier. Okay, so the second historical example I want to talk about is the atomic hypothesis. The hypothesis that all matter is made of atoms, and that the behavior of materials can be explained as being the aggregate behavior of atoms in their various organized forms. Are you familiar with this? I assume you might have had, say, chemistry in school.
Yeah, yeah, no.
Okay, right. So an example of this would be, the earliest example of this, or some of the earliest examples would be the idea that if you inflate a balloon, there's a pressure inside the balloon that keeps it inflated, and that this pressure is due to the fact that there are atoms or molecules of air inside the balloon, and they're moving around rapidly, and they're banging against the walls of the rubber walls of the balloon, and exerting a tiny force on the balloon that's keeping it inflated. Okay, so this idea, this is called the kinetic theory of gases, and so it's the idea that air can exert pressure on things, and that pressure is due to the fact that the air is made up of invisibly small atoms or molecules, and that they're moving around rapidly and colliding with whatever they're in contact with. Okay, so I guess I double-checked the history this morning. Apparently, the first proposal for the kinetic hypothesis goes back to the middle of the 1700s, but it was formalized mathematically in the mid to late 1800s. Okay, so the two names that are often associated with the formal statistical description of a group of atoms that are kind of rocketing around in a container goes by the name of the Maxwell-Boltzmann distribution, or the Maxwell-Boltzmann statistics. So James Clerk Maxwell, who published his work in the middle of the 1800s, and then Ludwig Boltzmann, who published near the end of the 1800s. So do you know those names, Sam?
Oh, sure. Maxwell's
Okay.
equations. Yeah.
So do you know? So Boltzmann, in particular, really felt that having written this very detailed mathematical description, not just of how the atoms, not just the hypothesis that the pressure of a gas is due to the motion of the atoms inside the gas, but he wrote this very detailed mathematical description of how different atoms would have different speeds, and how if you increase the temperature, the average speed of the atoms goes up. And if you decrease the temperature, the average speed of the atoms goes down. And so temperature is actually a measure of the energy content of these atoms and molecules as they rocket around inside the container. He thought that in doing so, he was definitely proving the existence of atoms. But there was a philosophical school that really put him into a depression, because they insisted that he had come up with a nice idea, but this absolutely was not proving the existence of atoms. So do you know anything about that history?
No.
Oh, okay. So the only name I know that's associated with this is someone named Bloch, Bloch. But there was a whole school of German philosophers who basically said that mathematical theories would never constitute a proof, that you had to be able to see something with your own eyes.
Oh. Well, I know that idea very well. I wrote
Yeah.
my dissertation basically on someone with that view.
Can you want to tell
Empiricists.
us a little bit more about it?
Well, just the idea that things that are, well, I mean, exactly what she said, that sort of modern empirical views, or one version of modern empiricism says that we can't infer the existence of unobservable entities, things that we can't see with our own natural faculties.
Oh, okay. And
Um,
is there special, like the fact that I'm wearing glasses, would that rule
well,
things out?
yeah, that the glasses are fine. um, because you can walk closer to something. Like looking through a telescope at the moon of Jupiter actually doesn't count. That counts as observable because you could go up to Jupiter and see it in person. So
Okay.
it's whether it's in principle undetectable by human faculties. So a microscope at a certain level of magnification would, starts to count as unobservable. But you can imagine there's a big debate about that.
Yeah, I mean, there's some gray area. I mean, like if you built a virtual reality of atoms on a surface of a table, for example, uh, I mean, because that's being mediated by computers and electronics,
Yeah,
and
no, that doesn't count as
that's no good.
observation. No.
Okay, yeah. So Boltzmann in particular. I mean, James Clerk Maxwell did many, many amazing theoretical accomplishments in the middle of the 1800s, and he never let himself be bothered by people who didn't like his ideas. Like he was not a moody individual. Among other things, he also explained the many of the things we take for granted today about electric and magnetic fields. He's the person who first showed that electromagnetic waves were what we call light. So he gets credit for that as well. But Boltzmann, on the other hand, was prone to depression, and he felt that he had proved the existence of atoms with his mathematical theory, and when he ran up against these very influential philosophical figures claiming that he hadn't proved anything, it did send him into a depression. He did ultimately take his own life, although my understanding is that he also suffered from kidney stones. And so I have to admit that if someone saying that someone took their own life because they had some professional frustrations and they had kidney stones, I mean, to me, the kidney stones feels like a more proximal cause. But regardless, that was a source of frustration for him. So, but anyway, let's just taking that specific example. Let's compare that to the scientific method again and see how far we get.
Okay, sure.
Right.
Um,
So, what was the observation? Well, actually, there were a bunch of different kinds of observations. So, Boltzmann was not an experimental physicist, but the observations of pressure that a gas would exert pressure on the wall of a container that was already well known. So, the concept of hydrodynamic pressure or hydrostatic pressure, those were already established in the 1800s. There were also other pieces of evidence that matter might be made of discrete objects that combine in very specific ways from the burgeoning field of chemistry. Okay, so in fact, by the time Boltzmann was doing his work, there was an early version of the periodic table that was already in existence. So the idea never mind the idea that there are atoms, but the idea that there are specific kinds of atoms and different atoms can form combinations in different ways. So, for instance, the idea that water is two atoms of hydrogen and one atom of oxygen, H2O. That already existed at the time Boltzmann was doing his work. So the idea that atoms are real, it wasn't just Boltzmann's mathematical explanation of gas pressure. It was also arguing that, hey, chemical reactions not unfortunately not always, but often seem to obey a rule where elements combine in integer proportions. Okay, so that was the set of observations. The explanatory hypothesis is that everything is made of atoms, and that there are different kinds of atoms, and that these atoms can combine in very specific ways. And then the experiment. Well, again, Boltzmann was not an experimental physicist, but he he was building his hypothesis on the back of really 100 years of thermodynamic experiments, and also let's call it 50 or 100 years of chemical experiments. So he didn't design any new experiments, though, to test the existence of atoms. So where do we stand? Like, so if you come up with a new theory that retroactively seems to explain a lot of experiments that until now had been somewhat disconnected, where does that land in the scientific method?
Yeah. I mean, there is actually debate in the philosophy of science. There's a difference between prediction and retrodiction.
Okay.
And so prediction is when you don't know the answer and you formulate your hypothesis and you do the experiment. And that some people think that carries more evidential weight. And retrodiction is when you have all the experimental data already and you're looking for a hypothesis that unifies and organizes it. And these same people think that that has less evidential weight because you can kind of cheat. Like you
Yeah,
know the
right.
answer already.
You
Right.
can
So
always
the
tweak your
Eddington
theory.
eclipse expedition, where Einstein predicted, made a prediction, and then Eddington confirmed it with this observation of the solar eclipse. That's a perfect example of prediction because Einstein did not know what the answer was and didn't kind of massage the theory to fit the data. Einstein
Right.
made a very bold claim.
Just to unpack that a little bit more for the listeners who might not be familiar with this test, in the early 20th century, Einstein published a theory of gravity, which predicted that gravity would bend light rays and could basically act like a lens under certain circumstances. And then one way to test this would be to go to a place where there's a solar eclipse happening. And at the peak of the solar eclipse, you can see stars in the neighborhood of the sun. And you can try to measure whether the positions of those stars has been changed by the gravitational lensing effect of the massive gravitational field of the sun itself. And Eddington did exactly this and made the observations and made the measurements and claimed that his observations were consistent with the predictions of Einstein's theory. For what it's worth, my understanding actually is that Eddington's claim was a little bit stronger than the data justified. I believe there's some controversy about whether Eddington's data actually proved general relativity or not. But I think this is a more recent controversy.
Okay.
Did you? Yeah,
I haven't
yeah,
heard of that.
yeah, yeah, yeah.
Yeah.
I mean, we've now observed gravitational lenses through our telescope, in, I'm going to say tens of thousands or hundreds of thousands of various situations. So that aspect of the theory is definitely confirmed by modern telescopes. But in 1922-ish, it was that was not the case. No one had ever seen a gravitational lens before. So retrodiction is a bit more problematic. And actually, I'm going to agree with that because speaking as someone who's written a lot of theory papers over the years, I'm familiar with the fact that you can always try to customize your theory to fit slightly uncomfortable facts. And it's a tendency that theorists always have to draw their own sort of personal line. It's like, how far are you willing to modify a theory before it just does begin to feel like, you're not really advancing the cause of science anymore. So, I mean, but now let's just revisit Boltzmann's hypothesis, which is that everything is made of atoms, etc. There have been more modern experiments, but relying on more modern tools that do seem to remove any doubt. Okay, so for me, there's a new kind of microscope that was invented. Oh, I want to say 1980s, 1990s, called the atomic force microscope. And these microscopes are essentially tiny needles connected to a massive piece of machinery that will allow the needle to move tiny distances and move up and down tiny amounts. Literally, distances and height changes that are comparable to the size of individual atoms.
Wow.
And so by dragging this needle across the surface, back and forth, you can actually see these little bumps.
Oh my gosh. Yeah, I didn't know this.
Yeah,
Cool.
yeah, and I mean there are variations on this technique, but yeah, so you can actually see little bumps, and and by dragging the needle back and forth, you can build up a picture and actually see atoms on a surface. It doesn't. I mean, the atoms have to be pretty robust. They have to stick to the surface, and they have to be able to withstand the fact that you're dragging a needle over them. But yeah, so you can actually visualize. So actually, you can use this technique to visualize various chemicals too. So you can actually confirm not just the existence of atoms as these little bumps, but you can actually confirm that the atoms are arranged in certain ways
Hmm. Oh, wow.
in some cases. So the atomic theory was, I mean, throughout the 20th century, it gradually transitioned from being something which was really only something which had explanatory power if you used a bunch of math, to something which over time the sort of the more what I want to say objective reality of the atoms became harder and harder to dispute. Um, what you said that the empiricist, because you're using a microscope, the empirical school of philosophy would still deny the existence of these
Yeah,
atoms?
there are some people, and just as a matter of logic, if you have, I mean, the old logical positivist idea was like there's the observation language and the theory language. More modern way that doesn't work at all. You can't really disentangle observation words and theory words, but the modern version is that you have models, and some parts of those models, according to science, are observable by humans, unaided perception, and other parts are not. And if you take the parts of the model, say the atomic theory, take the part of the model that's observable by humans, including the output of the microscopes that you're talking about.
Yeah, I mean, I want to be
And
clear about this. I mean, I do feel, I mean, for me, I feel like the atomic force microscopy results. I mean, you could just literally just have a picture of atoms arranged in a material on a surface. Um, I mean, to me, that would like to me the German philosophers who made Boltzmann depressed in the first place. It's hard for me to imagine that they would still complain if they essentially had a photograph of atoms on a table.
well, the guy I wrote my dissertation on would complain, and that's because you have a theory that's modeling the universe, and then there's the parts of the theory that are observable by humans. There's So keep the parts that are observable by humans the exact same. There are multiple kind of unbounded ways of theorizing the unobservable parts of the universe such that you get exactly the same result.
I mean, okay, so I guess actually this is as good a place as any to mention that if you have a set of results, I agree, there are always going to be an infinite number of distinct mathematical theories that will explain the same set of results.
Right.
And so scientists have early on, scientists invented a way of picking the best mathematical explanation, and that technique is to simply choose the simplest, the one with the fewest adjustable parameters.
Yeah.
So if you have a theory of gravity with that you can write down using three mathematical symbols. And then you have a competing mathematical theory that requires, 20 pages and dozens of mathematical symbols. They give identical predictions, or they match all known observations of gravity, then we're going to go with the simpler one, the one line explanation. That goes by the name of Occam's razor.
Yeah. Yes. And modern empiricists would say, on what grounds do we think the universe is more likely to be simpler than not?
Oh, so they don't accept Occam's razor.
Oh, no. They say
Oh, okay.
that's, you know,
Yeah. So, I mean, if you
maybe
don't
good
accept,
for us. Like we work with the simpler theories because the math is easier or whatever, but there's, no reason. I'm trying to remember the quote, but it's something about like, unless you believe God created the universe so that it's easier to understand by us or
oh,
something, it's just completely parochial. Why would the universe be more likely to be simpler than not?
Oh, that's really interesting, actually,
Yeah, it makes
because
sense. So
I mean,
yeah,
right,
no,
right,
these
because
they go
you
hardcore.
can't. I'm sorry, what was that?
They go hardcore on this.
I mean, right, I hadn't thought, right. So Occam's razor, I mean, so, right. So if you're a scientist who believes in in the explainability of the universe, then Occam's razor is essential. And if you don't accept Occam's razor, then suddenly anything goes.
Yeah.
Oh boy. Right, like
Yeah.
you can always come up, actually, you could, right, as you said, but earlier, in the case of Galileo and the aliens living on the moon, you could always come up with a conspiracy theory that
Yeah.
explains all your observations.
Sure.
Um,
Yeah.
yeah, so I guess it is, but oh, right, so right, I'm a career scientist. So as a scientist, I like to think that the objects of my study are real and are explainable,
Yeah.
and that I mean, Occam's razor won't always give the right result, but that most of the time Occam's razor will give the right result. Right in this, I mean, we can actually, we aren't going to go down the rabbit hole of what is the definition of scientific truth. Maybe that's another episode.
Yeah. Yeah. No.
But yeah, but this is all, but this does circle back to this question of, what is the scientific method? And does it represent what scientists actually do? Or how accurately does it represent what scientists actually do? Of course, the scientific method says, come up with a hypothesis, test, build an experiment to test the hypothesis, and then refine your hypothesis. The scientific method technically doesn't say anything about whether we're exploring the actual truth in quotes or truth with a capital
Right.
T of the universe.
Yep.
I mean, you could make a kind of utility argument where it's, science becomes more and more useful over time. It doesn't necessarily become more and more truthful over time, but its utility expands. We can build better tools. We can build faster computers. We can build more efficient solar panels. We can come up with better medicines. Right, none of this actually. These are all almost questions in engineering, right? They're not questions about whether atoms actually exist or whether Jupiter actually has moons.
Yeah.
Okay,
Well, so I have a couple examples, and you
yeah,
can correct
please.
my history, but one of the things I'm interested in, we've talked about the other parts of the scientific method, but is this refining the hypothesis. And the way I learned it, it's, the experimental result decides whether the hypothesis is true or not. So
Okay,
it's more definitive than refining. And so, you're talking about iterations, which I think is way more realistic. But the way I was taught it was
yeah,
like
no, I
crucial
agree.
experiments.
Sometimes it's said that you find you you build a controlled experiment, and then at the end of your experiment, the hypothesis is either true or false.
Yeah, exactly. And so I am intrigued by, and this is coming from Thomas Kuhn, there's some instances in the history of science where scientists just don't seem to care that the hypothesis is refuted by the observations.
Oh, yeah, actually, okay, well, actually, do you want to give an example? I could probably dig up a couple.
Yeah, yeah. So I think there's examples I have, I believe, both in Ptolemaic astronomy and I believe, in Newton's theory of gravity.
Oh, wait, hold on. You forget, you have to explain what Ptolemaic astronomy is if you're going to mention it.
Okay, well, just the idea that the Earth is at the center. It's just another
Okay.
word for what you were talking about. The Earth is at the center of the universe, and planets were orbiting the Earth on these perfect spheres. And there's this idea that went back to Plato and Plato's idea of perfection, which is exactly where I think the idea that the moon had to be a perfect sphere came from.
Oh, yeah, we haven't talked about
Yeah,
what the ancient Greeks thought.
yeah,
But yeah, the idea was that the Earth was not perfect, but everything in outer space was. So perfect
right.
spheres, perfect circles, perfect in a geometric sense.
Right. And so that kind of Platonism combined with Christian theology, the idea of a perfect being, is another example of the way that the Greek idea of perfection kind of influenced Christian theology, which of course influenced the Catholic Church. In any event, in Ptolemaic astronomy, they would put the planets on epicycles, and
Oh
the way
yeah,
they would explain why planets seemed to, from our point of view, to speed up and slow down and go backwards, was that they were on circles, perfect circles that are attached to perfect circles, and so they
yeah.
have basically two motions. But some of these models involve that the planet would like really vary in its visible size, which it does not.
Right. Yeah. So just to unpack that a little more. So this is an example of how when a set of observations don't match turn out not to match a simpler version of the model, you make the model more complicated, uh, and rather than rejecting your original hypothesis, right? So if your hypothesis is that all motions in outer space are governed by perfect spheres and perfect circles, if you make an observation that indicates that that seems difficult to explain on this hypothesis, then you kind of double down, right? So one of the classic examples was if you watch the motion of Mars from night to night against the constellations. So every once in a while, Mars sort of reverses direction. It's called retrograde motion. So that if you're tracking the motion of Mars, it's, maybe it's always moving from night to night, it's moving across your star map to the right, to the right, to the right. But then suddenly, across your star map for a few nights, it moves back to the left before resuming its rightward motion. And so that is hard to explain in the context of everything just going around the Earth in perfect circles, right? Because how does something go backwards if that's the case, right? So what you do is you add in an extra circle. And so you say Mars is on that extra circle, and so sometimes under just the right conditions, it appears to us to be moving backwards. Um, you know,
And then if I can add like a more challenging one, I think, because it's based on a theory that we think was really on the right track. My understanding is that Newton's theory really people didn't figure out how the moon was doing what it was doing for a
oh,
long time.
oh, are you talking about tides?
No, no, just the actual orbit of the moon.
Oh, you might be thinking of the precession of the orbit of Mercury.
No, no, I
Okay,
think
I may
literally,
not know the example you're referring to then.
yeah, I mean, we should put a thing in the notes or something, but my understanding is that it took a real, because it's so complicated, so close to the Earth, and there's so much involvement between the gravitational fields that Newton's theory wasn't getting the right answer for where the moon should be for a
I know what you're
long
referring.
time, and people just ignored it because it was obviously such an awesome theory.
I
Just
think
ignore.
I think I know what you're referring to. Yeah, actually, when Newton was doing his work, one of the well, actually, this was one Newton delayed publication of his research for almost 20 years because he had a bad value for the distance between the center of the Earth and the center of the moon. So as a result, So he was like right. We know the moon goes around the Earth in about 28 days. And he wasn't getting 28 days. And it's this, if his theory wasn't predicting 28 days, then, I mean, that's one of the most obvious things in the night sky. So it had him extremely concerned. So he waited 20 years to publish his work because he just had a bad value for the distance of the moon, and eventually someone made better measurements of the distance to the moon. But even after he published I don't know this part of the history, but it's possible that even after he published, he did not have a great prediction for the length of a month.
Okay, yeah,
Yeah.
my memory of this is a little fuzzy, but
No, no,
but
I certainly believe
this,
that
yeah, this
we
idea
know
that
that. Yeah,
scientists will sometimes ignore disconfirming uh, results
yeah.
because maybe there's not another competing theory around, and because the theory is so productive in other areas. So this idea that you do an experiment, it gets the wrong result, you reject the theory. It's not true.
Yeah.
Scientists are very conservative in rejecting theories, which is good, because it
Um,
took a long while to come up with them. Paraphrasing Kuhn there.
I actually have my own theory of scientific progress. I call it the three nails in a coffin theory of scientific
Oh,
progress.
okay, cool.
Tell me if you've ever heard this before. But the way science actually works is a theory isn't dead until there's three different kinds of evidence
Hmm.
that point that three, not just three different experiments, but three different kinds of experiments that seem to all disprove it.
Hmm.
Yeah, I mean, the thing is, it's not very philosophically satisfying because like three seems like such a random number. But I think in practice, scientists often wait until they've seen more than one kind of experiment that also disproves a given theory,
Okay,
right?
not just
So
a just
yeah, so one counterfactual from one branch, one kind of experiment. If a theory is productive in other ways, we're not going to throw it away because of one new tool, typically. But if there are maybe, but if there are three different kinds of tools that are all saying that the theory just doesn't work anymore, then there's really no sense trying to salvage the theory. It's time for a new theory.
hmm. Oh, cool.
Um, Yeah, so this is a difference
That's
between the
fun.
way scientists actually do that. Because remember, again, isn't science as practiced is really not focused on truth with a capital T. It's just focused on progress, on whether that be material progress like engineering or just explaining the results of more and more experiments. So I mean the three nails in a coffin approach to ruling out theories is it just means that your theory is just becoming less and less useful over time. So again, utility is often the final arbiter in situations like this.
Cool. Well, I think that might be the perfect place to wrap up, and we're just about at our time for
Oh yeah.
recording.
Okay. Well, I had so much more to talk about. We will have to talk about this again.
Okay. Well,
Um, but yeah, so I'm Eric and you're Sam, and we have been the Boltzmann Brains.
yes.
Uh, Bye,
Thanks for
everyone.
listening.
Thank you for listening.